Hello everyone! In this video we're going to go over the common interview question 3-sum. The question states, given an array nums of n integers, are there elements a, b, and c in nums such that a plus b plus c is equal to 0? We want to find all unique triplets in the array which meet such a condition. Now let's quickly go over an example of the question and then go over some conditions we want to clarify with the interviewer before we make any assumptions. So one example with this given array of -1, 0, 1, 2, -1, and 4, a solution set might be -1, 0, and 1 because these three numbers sum up to 0. Now let's clarify some conditions. So we might ask, can we use the same number twice? So if we look at this array of nums, if we were to take out this -1, would this solution set still be valid? Because we would use this -1 twice, and we would use this number once. In this question, we're going to assume that the answer to this is no. Another question we might ask is, can we have duplicate triplets? So for instance, if we have a solution set of -1, 0, and 1, and another solution might be 0, 1, and -1, are these unique solutions or are they essentially the same thing? And for this exact condition question, we're going to assume that we cannot have duplicate triplets. Now that we understand and have clarified the question, let's evaluate some approaches we can take to solve it. One possible method is to use brute force to evaluate every unique triplet to see if the sum of the three are equal to 0. Now this would involve traversing the array in a triple nested for loop, as done so here, and checking to make sure that each triplet would be unique. And this would make our time complexity O of n cubed. And if we use a set to evaluate the unique triplets, our space complexity would be O of n. Now let's think of some ways we can optimize our solution. If we break down the question and we see that we only have two numbers to check to add up to a variable sum x, what we could do is we could sort the array first, then do a binary search to see if the two numbers added together equal a certain number. And we can do this when it's sorted because we can adjust the left and right pointers to change based on how far we are from a particular target sum. For instance, if our target here with two numbers was to be 1, we could see our sum with our left and right pointers here are 3. So because the sum is too large, we can decrease the right pointer left by 1. So now if our right pointer is pointing at the next element, we see that our sum is equal to 1, which matches this one. Now how can we change this approach and alter it to fit the question we have so far? Well, we can still apply the previous approach to our current 3-sum question by sorting our array and systematically holding constant a starting point here while doing a binary search on the right remaining portion of the subarray. And we can systematically iterate the starting point while continuing to do a binary search on the right portion of the array here to check all possible triplets and to see if they meet our condition of summing to 0. Now, why don't we take a look at a possible example for our 3-sum algorithm that we just created. So first we hold our starter point constant here, and we want to perform a binary search on the remaining right portion of this array here, which means that we would have a pointer on our left here and a pointer on the largest point of our array, which is 4. And we could check the sum of the three numbers we have pointing at currently. So currently that's -1 plus -1 plus 4, which is equal to 2. Now we see that 2 is greater than 0. So our sum is actually too large right now. And what we do in a binary search is we decrease the largest point or the right pointer by 1 and check that iteratively to see if the sum is equal to 0. So we can see that if we were to de-increment the right pointer by 1, it would now point at 2. Now, looking at 2, we can see that -1 plus -1 plus 2 is equal to 0, which actually does fit our sum. So we could add this triplet into our solution array because the sum of the three numbers is equal to 0. And we would continue to do this for every combination of the triplet even after we found one triplet that meets the solution, because our problem defines our solution set as all possible triplets which sum to 0. So after doing this, we could actually increment and de-increment simultaneously the left and right pointer. So incrementing the left pointer, we'd be hit at 0, and decrementing our right pointer, we'd be at 1. And we can actually see that if we were to calculate the sum of the three numbers so far, so -1 plus 0 plus 1, we would also get a sum of 0 in this case, and we could add our three triplets into our solution set. So -1, 0, and 1. Now we can see that with our left and right pointer being next to each other, we can no longer iterate or de-increment our left or right pointer to analyze any more numbers. So our binary search for this particular right subarray is finished. Now what we do now is we want to increment our starting point by 1. So now what we can do is we can pick our next number here, which is also -1, as our starting point, and we can do a binary search on the remaining right portion of our subarray here. Now, I'm going to say you're going to immediately notice that there is something wrong with this problem. Now, if we were to hold -1 again as a starting point and do a binary search on our right subarray, we would see that we would eventually come to a triplet where -1, 0, and 1, as you can see, these three numbers, would also sum up to 0. Now, as we specified before, our triplet must be unique. So the fact that we already have a -1, 0, and 1 in our solution set means that we can't add a second one into our solution set. Now, there are two ways to solve this triplet duplication problem. The first way is to store our solution triplets into a set. And the reason this works as well is that the triplets are actually naturally sorted. And the reason is that our base will always be the smallest number, our left pointer will always be the middle number, and our right pointer will always be pointing at the largest number. Now, for this reason, our triplet solutions are actually sorted and stored consistently. So we can see here that we found that -1, -1, and 2 sum up to 0, and -1, 0, and 1 also sum up to 0. And we can see that this -1, 0, 1, which is stored the same way as this one, has already been added into our solution set. So naturally, this triplet would not be added as a result. Now, the reason why this solution doesn't always work with every problem in O of 1 space complexity, is that our return solution may ask for an array list of an array list. Now, what this would mean is that we would need to convert our set into an array list. And to do that, we would need to spend O of n space complexity creating a new array list and one by one converting our set into an array list. And in fact, even if you thought of this very smart way of converting a set into an array list, which is simply adding my set here, which would actually convert it into an array list in one line, it would still cost us O of n space complexity, and thereby not giving us the most optimal algorithm solution. Another approach we could take is to simply skip duplicate numbers when we increment or decrement our starting point, left pointer, and right pointer. Now what this would look like is if we had the array -1, -1, 0, 1, 2, and 4, and our starting point was here, and we want to increment it, we would check the next point and see if the point is a duplicate. We see that it is a duplicate, so we simply skip to this one without checking and doing a binary search with this other -1 as a starting point. So now our starting point would be 0 with a binary search of 1, 2, and 4. We also have to skip duplicates for our left and right pointers after they found a successful triplet which sums to 0. So let's take an example array and see what this looks like. So let's say we have -2, -1, which with -2 as our starting point, 0, 1, 1, 2, 2, and 4. Let's say that our left pointer is pointing at 0 and our right pointer is pointing at 2. And we see here that a successful solution set has been found with -2, 0, and 2. Now, if we were to decrement our right pointer, we would be pointing at another 2, and we would subsequently be adding that second 2 into our solution array. And actually, to make this example more complete, there should be another 0 here, so that the left pointer would also be pointing at the same number as well. So we see that if we don't skip the left or right pointer, we would possibly end up with the same solution set. And to avoid that, we also want to skip duplicates when decrementing or incrementing our left and right pointers. Now that we've discussed our solution, let's take a look at the code that represents it and go over an example that will illustrate step by step. So given this array nums, the first thing we want to do is sort it to set it up for our binary search. So sorting it ascendingly, we get the array -1, -1, 0, 1, 2, and 4. And remember, we can do this sort in n log n time. And since our iteration down here will take n squared, this sort will actually not affect the overall time complexity solution. The next thing we want to do is systematically define the point we'll hold constant while we do a binary search on the right portion of the array. And this number will go from 0 to 2 numbers before the end of the array itself. So in this particular array, it'll stop at 1. And the reason we have this is to leave room to make one full complete triplet before the end. So we see that if this 1 were to surpass itself and go past it, we would not have enough space to make a triplet. After we do that, as we discussed, we want to skip any duplicates for our starting point, and this is to avoid any duplicate triplets. Now you may have noticed we've added one piece of logic down here, which basically states that if our holding point is greater than 0, we can go ahead and break out of this loop over here and return our solution set. And the reason we can do this is that the holding point, because it's the smallest number, should not be greater than 0. Otherwise, the triplet has no way of being equal to 0, since anything to the right of the holding point is positive. Let me illustrate this in a quick example. So let's say we have the array -1, 0, 1, 2, and 3, and our holding point is equal to 1. We can see that we're doing a binary search on the right portion of the array here, but there's no possible way that this triplet would sum up to 0, no matter how we adjust this binary search over here. Now let's go ahead and illustrate the rest of the steps in variables as well. So we can see that our holding point starts out at 0. Our left number here is equal to the index of the smallest number in our right subarray, which is currently from 0 to 4, with our holding point being set at 0. So our left indice which is I plus 1, is equal to 1. And our right pointer, which is equal to the index of the largest number in our right subarray, is equal to 5. So we see that our left pointer is pointing at -1 as well, and our right pointer is pointing at 4. So we see that the left and right pointers here demonstrate the boundary of our binary search. Now we can go ahead and perform the binary search itself in this while loop here. So the first thing we want to do is calculate out the sum. So we see here that the numbers at the indices of I, left, and right are -1 plus -1 plus 4, which is equal to 2. So 2 is our current sum. Now we see that sum is greater than 0, so we want to de-increment right in an effort to decrease our sum and get it closer to 0 if possible. So let's go ahead and do that. So our right pointer is now pointing at 2. And our indice is now equal to 4. So repeating this while loop, we see that the left is still less than the right pointer. And our sum now is -1 plus -1 plus 2, which is equal to 0. Now we can enter this sum equals 0 body down here. And so the first thing we want to do is add it to our solution set. So we can add -1, -1, and 2 into our solution set down here. After doing that, we want to skip any duplicates in our left and right pointers, as we indicated before, to avoid a duplicate triplet. So we can see here that the next number is a 0, which is not equal to our current left pointer. And similarly, the next number for the right pointer is equal to 1. So we also see that that's not equal to our current right pointer number. So we can we can increment and decrement respectively without skipping any numbers. So our next numbers are 0 and 1. So now, let me just go ahead and update our pointer list down here. So now our left pointer is pointing at 2, our right pointer is pointing at 3, our holding number stays the same. And our triplet down here is -1, 0, and 1. And we can see that the sum down here is actually also equal to 0. -1 plus 0 plus 1 is equal to 0. And we can add it to our solution set down here. So we can now add -1, 0, and 1 into our solution set. Now we can sort of see trivially that there are no duplicates, and in fact, if we increment and decrement our left and right pointers, they'll end up being 3 and 2, which does not fulfill this condition up here. So we want to now break out of this while loop and move on and iterate to the next starting point. So the next starting point would now be 1. So this would now point at -1, and our triplets and our left and right pointers would be updated respectively. But we can see, as we discussed before, that this -1 is equal to the previous -1, and that this piece of logic down here will prevent us from doing the same iteration. Now, to quickly demonstrate what would happen if we did analyze this, is that our left and right pointers would eventually be pointing at -1, 0, and 1 again, because this right pointer would continue to shift down like this and eventually point at this 1. And we would be forced to add this -1, 0, and 1 into our solution set, causing a duplicate triplet, which we don't want. So rather than allowing that to happen, we can skip this -1 down here. So we can actually change this 1 or this I to a 2 and have it point at 0. And we can do a binary search on this right subarray here. So our left pointer is now pointing at 1, and our right pointer is now pointing at 4. So our triplet now is 0, 1, and 4. Our left indice would be 3 and our right would be 5 as well. So now we can see that the sum is equal to 5, since 0 plus 1 plus 4 is equal to 5. And we see that that sum is greater than 0, so we want to decrement right. So now decrement right. The right pointer is now pointing at 4. And now our triplet is 0, 1, and 2. However, we can still see that the sum of the three numbers is still greater than 0, since it's 3. Now, because it's still greater than 0, we need to decrement the right pointer. And we can sort of see trivially, without even doing any calculations, that our right pointer is now equal to our left pointer. And this now breaks this condition here for our binary search. So now we need to increment our starting point again. We see that our starting points are now pointing at the indice, third indice. So the starting point is now pointing at 1. Now, remember what we talked about before with this breaking condition here, where if our holding point is greater than 0, we can go ahead and break out of our for loop. And we do see that our holding point is now pointing at the number 1, which is greater than 0. So no numbers past it can be equal to the negative value of this starting point here. So we can just return this solution right here. Now I want to take some time as well to analyze the time complexity of this solution. As I hinted at before, it is n squared because we're traversing the array once up here n times, and within this array over here, we're also traversing it n times since we're doing a binary search on the right portion of the array. So with that, we get n squared. Although this little hack down here doesn't actually change our time complexity, it does technically change the runtime of the algorithm. So on Leetcode, your solution might run a little faster, but our time complexity would remain at n squared. And since we didn't use any additional data structures, our space complexity would be O of 1. Now, if we had used a set to determine whether or not a triplet was a duplicate, we would need to convert that set into an array at the end, and thus cause this space complexity to be equal to O of n. And that's why we used the skipping method technique. Thank you so much for watching, and I'll see you in the next video.